Okay. So as I've stated, we have we've learned essentially the laws that govern gases. First, we learned all the different relationships: Boyle's law, Charles' law, Gay-Lussac law, put together as the combined gas law. And then on Friday, we talked about, instead of a changing situation from this temperature, pressure, and volume to a new temperature and pressure and volume, which is the combined gas law, we've defined the gas in terms of pressure, temperature, volume, and moles, and we put that all together in what is called the ideal gas law. And that essentially allows us to determine the number of moles in a substance, in a gaseous substance, knowing the pressure, the temperature, and the volume. And we did all kinds of practice problems on it. And that essentially is all we need to know about gases, because now we have the ability to deal with moles. We could now do some chemical reactions, and we could actually do a lab. We might be doing one on, it might be tomorrow for the second half of the class, and it won't be an official lab write-up. It's a lab I've wanted to try, so it might be just a do it, get some observations, and do some simple calculations. So it might be just an activity with a little calculations on the end. But now we're ready to actually do some stoichiometry. But before we do that, we've got to talk about how we practically collect gases in an experiment, because gases are different than precipitates. Precipitate forms and it settles to the bottom of your aqueous solution, and you filter it off, and you've got it quite easily, right? So if solids are formed, they're really easy to gather up. We did an experiment where we heated sodium bicarbonate. We didn't have to do anything in the end to find its mass, because the solid was sitting there in the test tube. All we had to do was weigh it again. So how do we gather gases, and what are the practical problems that are associated with actually gathering gases? So that's what our first little PowerPoint is on today, vapor pressure and Dalton's law of partial pressure, and it's more of a discussion on how we practically collect gases. And then we have a second one, which is something called molar volume, and that deals with kind of simplifying the ideal gas law to make it more useful. Okay. So first we'll talk about vapor pressure and Dalton's law of partial pressure, and let's talk a little bit first about mixtures of gases. So I've already tried to express this to you a little bit as we've encountered the various gas laws. In many of our questions, the question doesn't even include what the identity of the gas is. And that's because all gases behave the same way. Whether it's, and I said this the other day, whether it's a helium atom, He, all by itself, or whether it's a carbon dioxide molecule, or whether it's a great big molecule like maybe some evaporating gasoline that contains like 8 carbons and 18 hydrogens. As long as they're in the gas state and they're behaving like an ideal gas, they will exert the same pressure. Given the same temperature and volume, they will behave identically. There is no distinguishing between particle A and particle B when it comes to pressure. Everything exerts the same pressure at the same temperature and at the same volume given the same number of moles. And that's what this first statement says right up here. John Dalton hypothesized that gas particles in a mixture behave independently. And I described this to you when we first started talking about gases, right? A gas is a state of matter where there's so much room between the particles that they travel along in a straight line until they run into the wall or they run into another particle. And in order to be an ideal gas, they don't interact. The only way they interact is by a blind collision where they just bounce right off of each other and away they go. And so whether it's bouncing off of a helium molecule or atom, or it's bouncing off of a carbon dioxide molecule, it makes no difference. So gases behave as if they're on their own, as if they're just existing on their own in a big space, no matter how many gases are in that space. And that's what John Dalton hypothesized. The pressure exerted by a gas is the same whether it exists in a mixture or by itself in that space. So we have a term then called a partial pressure. If each gas then exerts its own little pressure, whether it's alone or not, we can then divide up a mixture of gases into its own little fraction of the pressure. That then eventually results in the overall pressure that we experience. So a partial pressure is that individual pressure that a gas would be exerting on a surface if it were by itself. So we then could analyze something like air. Actually, we'll write down Dalton's law of partial pressures first, and then we'll analyze air as a mixture of gases. Now, no need to draw the diagram or anything, but it's just a simplistic diagram that kind of illustrates what's going on in this equation. This image here is simply just cut and pasted out of your textbook. And it simply says the total pressure of a mixture of gases is equal to the sum of the individual pressures, the sum of the little partial pressures. So if I have a mixture of gases, I can add those individual pressures up, and it gets me the total pressure. This image here essentially states that, okay, if I've got some oxygen in a tank here, and I don't know if you can see the little measuring device here, but right there that says 3, right, as if there's 3 pressure units. And if we then had some helium which has 2 pressure units, and we could somehow get all of the oxygen and helium into the same tank, then these particles will bounce around as if they're on their own in their own individual tanks. Oxygen will bounce off of the walls. Helium will bounce off of the walls. They won't be aware of the presence of each other. They'll be just doing their thing, But in the end, the pressure in the cylinder will then be 5 pressure units because each gas will be exerting its own individual pressure against the walls, and therefore we can simply add up the partial pressures to get the total pressure. All right? So that's what Dalton's law of partial pressure simply states. Each gas behaves on its own, so if you want the total pressure, we can add up all of the individual pressures of each gas. A good example of that is our atmosphere. You don't need to rewrite the equation there. I didn't even realize it was there, but you can make a statement of that, or you can write the rest of it. But our atmosphere is a classic example of the law of partial pressure. Here I have the top 4 constituents in the atmosphere. And these top 3 are pretty constant. The amount of nitrogen in the atmosphere does not change by much. So this is P with a subscript, and that's supposed to be N2. That represents the pressure of the nitrogen. But I can't have a subscript on a subscript in PowerPoint, so that's why the 2 is big compared to the N. (79.10 kilopascals of the atmosphere is due to nitrogen. Oxygen, 21.22 kilopascals of the air is due to oxygen. Argon is the next most abundant, 0.942. Argon's a noble gas. It's just argon atoms hanging around in the atmosphere. Carbon dioxide then is number 4, and its value, as you probably know, is slowly increasing. People driving cars, cutting down trees, burning fossil fuels in electrical generation, all that good environmental stuff. I'm not going to have a big debate on, greenhouse effect and environmental this or that. We've talked a little bit about why carbon dioxide is very good at absorbing that heat because it can vibrate in many different ways. We've talked about the greenhouse effect. Here I want to just talk about the fact that there are these partial pressures. Now there are also many little very small constituents of the atmosphere that are changing depending on the situation. Water vapor is in the air for a short period of time because it rains out. We say it has a short residence time in the atmosphere. So it's very humid out there right now. So therefore, we have high concentration of water vapor. But change the air mass, weather comes through, it rains out, and that changes. Have we totaled up our partial pressures? What do we got? 101.3 kilopascals, which we already know is our standard pressure. So 101.3 kilopascals. Okay? So there's a little application of partial pressure. Now, why have I introduced you to this idea of partial pressure? Well, it has everything to do with the way we collect gases in the laboratory. So let's talk about how we collect gases in the laboratory. First, I need to talk about something called vapor pressure. At any temperature, all liquids evaporate to a certain extent. The vapors produced are in the gaseous state and thus produce a pressure. So right now I took some water and I put it into this beaker, and that water is trying to evaporate, all right? And some of it is successfully evaporating. I'll tell you that right now. We can't see that. But if I could somehow maybe cool off the sides of the glass, we'd get some of that water vapor sticking to the side and we'd see it kind of as a fog, all right? But right now, there is some water evaporating. And if it's turning into the gaseous state, then it's going to exert a pressure. It's going to exert a certain amount of pressure in that space above, because there's now going to be gas particles of water in the air, and it's going to bounce off of the surface of something, and it's going to exert a pressure. Here's a way in which scientists can determine vapor pressure. Now, obviously, it would take a lot more complicated apparatus, but if we took some liquid and we somehow evacuated it, and then put one of these pressure sensing tubes, this manometer that we've seen in our different simulations, it's just like Torricelli's barometer, and we let some of that vapor evaporate, because it will naturally evaporate, then there will now be particles in the gaseous state that will then bounce off of the container, which will cause a pressure. It'll also bounce off of the surface of, if it were a true manometer, it would be mercury. That would push some of the mercury down and some of the mercury up, and we could measure how tall this thing would lift, and we would get a pressure in millimeters of mercury if we had mercury in there. We literally could measure that, and it would truly be millimeters of mercury pressure. And that pressure would come from the evaporating liquid. So all liquids evaporate to some extent, and it exerts a pressure, and we call that vapor pressure because it is vapor coming off of a liquid, okay? Now this vapor pressure is temperature dependent. The more you heat this, put it in the sun, the pressure would increase. You'd have a greater vapor pressure. More would evaporate, all right? If you heat something so much to the point where it boils, it means that you've increased the vapor pressure so much, you've actually made it greater than the atmospheric pressure, and so it vaporizes so quickly, big bubbles of it come out. That's what boiling is. Boiling is the temperature at which you've made the vapor pressure of the water the same as the atmosphere. Right now, you can think of this liquid as not boiling because, well, you would say that it's too cold. But I could think of it not boiling because the atmosphere is actually pressing down on the surface so hard that the liquid can't escape easily into the vapor phase. If I increase the temperature, now the vapor is going to push harder up with a greater vapor pressure. And as soon as I get to the boiling point, its vapor pressure up is now equally as strong as the atmosphere's pressure down, keeping it in the liquid state. And when you get to that boiling temperature, the vapor pressure gets so great, it just comes out very quickly into the gaseous state, and lots of it vaporizes. That's really what boiling is. When the vapor pressure gets so great that the atmosphere can't hold it in the liquid state anymore, and it boils. We're not worried about boiling here, but that's just a little example of vapor pressure. In this case, we're worried about vapor pressure because we collect gases by pushing water down. It's called the downward displacement of water. So let's talk a little bit about how we collect gases. So you can write that big paragraph down. Don't worry about the table. That table is cut and pasted from the textbook. And if I'm asking you to do a calculation and you need a vapor pressure, I will supply you with those numbers. So don't worry about writing any of that data down in the table. That's really just for the purpose of us looking at a problem here as an example. Now this little picture that I've drawn here is a very crude representation of this device here, which is simply a water trough. All right, so that bottom little bowl, side view of a bowl here, represents, like I said, a very crude representation of a water trough. And there's actually a technical term for that water trough. It's actually called a pneumatic trough, with pneumatic representing gases, right? When the first tires were invented for the first cars, they were first all made of solid rubber. You know, like tricycle wheels? You know, like a tricycle wheel versus an actual bicycle wheel? A tricycle wheel tends to be hard rubber, solid. A bicycle wheel has air in it, right? So that's called a pneumatic tire because it's got gases in it to keep it inflated. So this is called a pneumatic trough because when it was created, invented, probably by Lavoisier, he seemed to invent most of the chemical equipment we use, it was used to collect gases, right? So here's the way a pneumatic trough works. Here I've got a couple of gas jars. Now these gas jars are not graduated. They don't have markings on them so I can determine how much is in it. So if I were to collect gas in these jars, it would be probably to perform a chemical reaction as opposed to measure how much gas is being formed. Here I've got a gas collection tube, and it's kind of like an upside down burette. And the numbers, though, count the same way, 2, 4, 6, 8, 10, et cetera, down to 100 milliliters. And if I then fill this with air and get some gas to displace out of it, then I could measure how much gas was formed. And if we do our little experiment tomorrow, we'll use the gas tubes. But let me just show you how we deal with this type of thing. Now, I know I don't have my goggles on, but I'm just dealing with water. I'm just demonstrating how we collect gas. Filling a little gas jar here, overfilling with water, I can put a little piece of paper towel on the back end, or on the top end of this, make a nice little seal, and I can actually invert. And have I shown you that before? That's because there's no air in there. So the air pressure, just like when you pull the cup out of the tub, right? Air pressure is holding that little piece of paper towel in there. So I can slide that in and not lose any air. Oh, look at there. I lost a little bit. You see some air got in? That's no good. I'd have to redo that if I was doing the experiment. I could do the same here with our larger gas jar. So you fill the things you want to catch the gas in with water, a little overflowing with water. You put a little piece of paper towel on that. Again, you can invert that very carefully. Get that into the water, slide that out. And now you're ready, and I don't know where I'm getting those little gas bubbles. I get a few. But now you're ready to catch the gas. In this case, I'm going to be the gas producer. You probably Probably say that all the time. Gee, Mr. Sandy, you talk so much. Must be full of gas. Hot air? No? Anyway. In the pneumatic trough, there's a little groove in the middle that you can slide the hose that you're collecting the gas from, whether it's from a chemical reaction coming from a test tube or whether it's from a tank. It doesn't matter. But then you just position everything over top here, and then the reaction produces its gas. And you've successfully caught my bad coffee breath from the morning, right there. We could do some studies on it. See how stinky it is. Coffee breath is stinky, you must admit. Anyway, so now we've collected some gas. Now, if I wanted to measure how much gas I collected, I need to figure out, well, ultimately, how many moles are in there, right? If that came from a chemical reaction, I'd want to figure out how many moles of gas are in that. Now, in order to do that, I'd need the pressure and the temperature and the volume. Well, the temperature isn't too bad. It was bubbled through this water, and so its temperature might be about the same as the temperature of water, and I could stick a thermometer in there and read the temperature of the water. The pressure's not too bad. I'd have to make sure I equalize the pressure. I'll show you that in a moment. But once I've done that, if I equalize the pressure inside the glass to the pressure outside the glass, the atmosphere, if I equalize it, then all I have to do is read my barometer. And I've measured the outside pressure. Now, the problem with that, though, is because I bubbled that through some water, as I bubbled it through, and as the gas comes in, so as that gas comes in, so if we've got the gas, then as it bubbles in, as these bubbles rise up, they carry some water with them. So in the end, I have gas plus I have some H2O vapor in there, H2O gas. Because as the bubbles rise through the water, some of it evaporates. And it evaporates because of its vapor pressure. Which means when you're done collecting gas over water, you actually have a mixture of the gas plus the water. So if we were to write this out like Dalton's equation, we would have pressure total is equal to the pressure of the gas plus the pressure of the water. And you'll notice in this equation here, I've simply brought the pressure of the water to the other side to leave the pressure of the gas by itself, which means if I just want the pressure of the gas, I simply have to take the total pressure, the atmosphere, and subtract off the pressure of the water. So I need to do a little subtraction in order to do that. Okay? So that's how we get what the gas is. And that's the only reason I've taught you about Dalton's law of partial pressure and vapor pressure, so that we can figure out what the pressure of the gas by itself is. This particular device, the gas collecting tube, is a little different. What we're going to do there, if we get to it, you'll fill it completely with water, and we're actually going to be reacting some magnesium in some hydrochloric acid. So we're going to also be filling it with some hydrochloric acid. Again, we'll overfill it. And instead of using a gas collecting trough, we're going to use a larger beaker for that. In this case, we're going to use a rubber stopper because when we have the gas being produced, we want that liquid to come out the hole because I'm going to need the rubber stopper to hold in some magnesium here. With this one, you'll invert, and then with a little bit of dexterity, you'll get it under the surface and carefully let your finger out. And then with a retort stand, we will hold that in place, and hopefully our chemical reaction takes place and it bubbles up and we measure what that is. All right? I don't know if I could actually simulate bubbling in this guy. I don't think I could. I'd have to take the stopper off to cheat a little bit. Oh no, now I've got a mess. See if I can cheat. Let me take the stopper off. You won't be taking the stopper off to do this. Why did I put it on so hard? Goodness gracious. So I'll take the stopper off, and we'll pretend we're making some gas here. And there you can see we've caught some gas. I've actually gone too far because I'm past the 100. But here's how you equalize the pressure. what you'd need to do is get your finger on the end of it again. All right? And we need to put it in a cylinder, like a graduated cylinder, so we can move it up and down. Again, you need your finger in the end there. There, I didn't lose anything. And now the trick is, you want the level inside to be exactly the same as the level outside. So I move this up and down until I have the levels exactly the same. Because if I have it too high, just like the barometer, it means that the gas in here isn't at the same pressure as the gas outside, because the gas is able to push it up. But if I get it to the same levels, then it means that the gas inside is actually at the exact same. So once I've equalized it, I can read the volume, I can write down how much I've collected, I can write down the atmospheric pressure as the total, and then using the vapor pressure, I can subtract and get the value, all right? And we'll hopefully have time to do a little activity on that tomorrow. Okay, so let's do a practice problem with this. So here's just a bunch of water vapor pressure temperatures. Let's do an example problem here. And it's just one example problem that I'm going to be doing. Then I'm going to let you work for about 5 minutes or so, and then we'll continue on with what's called the molar volume. That, I just brought up the table so that we could read the partial pressure here in a moment. On a test, I simply put the partial pressure in brackets in behind it. I simply say the pressure of the H2O at this temperature is. So we've collected some gas, 273 milliliters. We collected it over water, which means we've pushed the water down. The temperature, 22 degrees Celsius, and the atmospheric pressure, 100.7 kilopascals. That's the outside, which means that's the total. What's the partial pressure of just the oxygen gas? Well, pressure of the gas, in this case O2, is equal to the pressure of the total pressure, the outside, minus the pressure of the water. Yeah, hard to see. We need a pressure at 22 degrees Celsius. There's 22 right there. There's our number right there. 2.64 kilopascals of gas gets into the tube at 22 degrees Celsius. So the partial pressure part of the question is really easy. The total minus the partial pressure, 2.64. This is a subtraction, so we don't keep significant digits, but we keep decimals. So I'm only going to keep one decimal because my least accurate one only has one decimal. When you add, remember, it's decimals, not significant digits. So what's my number here? Need a subtraction. Yep. 98 point, and I missed that last bit. 98.1 kilopascals. So that's only the oxygen, and that's good because if we want to know how much there is, that's all we care about. How many moles of oxygen were collected? Well, if we want moles, what equation do we have to use? What gas equation do we have that has moles in it? Pause for thinking in the past. Pause for thinking about Friday. Yep. Very good. PV equals nRT. Do I have the pressure of the oxygen? What number is going in for the pressure of the oxygen? Yep. 98.1. Volume of the oxygen. What volume was that oxygen found in? Yep. Yeah, good conversion. 0.273 liters. Must be in liters. And we're looking for R 8.314 on the back of your table if you can't remember it, but we'll use it quite a bit. And what do I need to put in here for T? Yep. 295, that's the 22 plus 273, right? 295. Now, I want to do C on this slide as well because I don't have enough room. So I'm not going to do the dividing stuff that I normally do. You go ahead and divide off. Tell me how many moles. I don't know if you guys are getting good enough, but if you've done enough of the practice problems, you're probably realizing you almost don't even need to rewrite. It's 98.1 times 0.273, and then anything else that's on this side is going to get divided off. Divided by 8.314, divided by 295. Again, if that's a multiple choice question and I don't need to see the steps, you write that out. You don't have to rewrite. Just figure out how to manipulate your calculator quickly to get that answer. What do we have for number of moles? Do we have a number yet? Yeah, Jenna, what do you got? 0, 1, 2, and everything has 3. Because we're multiplying and dividing, right, I need another significant digit, right? Not decimals, but I need another significant digit. 1, 2, 0, 9. So 121, 121, 121 moles. Don't like it? Nope, we don't like that number at all. What do I got here? 109. Whoa, 0.0109? Yeah. All right. Here we go. Jenna will never answer again. 109. We like that one? Okay. Now, very often, if we're comparing an experiment that one scientist did in one area compared to another area, we need to convert that gas to a certain standard value. So what if this experiment was done at SATP? What would its volume be at SATP? So when we say dry oxygen, it means we've subtracted off the water, and we want it at the second property of SATP. And so this can be done in a couple of ways. Now that we know the moles, we could stick it back into a PV equals nRT equation and solve for a new volume, or we could use the combined gas law, because I have a volume, a temperature, and a pressure, and I'm now going to have another temperature and pressure, and I could solve for volume. So because I have two conditions, one where the experiment we did in the laboratory, and the other one is the standard conditions, we can use the combined gas law for that. So let's go ahead and do that one. P1V1 over T1 is equal to P2V2 over T2. My first conditions can be all of the conditions that I started with. Pressure. Now, the pressure of the dry oxygen gas, 98.1. That's why we did this whole thing. 98.1. Volume of my starting gas, 273 milliliters. Because we're using the combined gas law, we could leave it as milliliters. We're just going to get milliliters at the end. 273 milliliters. T1. What's the temperature we did our experiment at? 22. It's got to be in Kelvin. 295. P2. What's standard ambient pressure? Yep. That's standard pressure. So it's the other one. Standard ambient pressure. Yep. 100. 100 kilopascals. We're looking for the dry volume, V2. That's what we're solving for. What's standard ambient temperature? That's the laboratory conditions. 25, right? Because very rarely do we keep the laboratory at 0 degrees Celsius. And I need it in Kelvin. Yep, 298. And I also do not have enough room on my slide to manipulate this. 298 has to come up top. 100 has to go down below. I'm just going to put a V2 equals, and I need you guys to finish that off for me. And because I left my volume in milliliters, I will have a unit of milliliters. Yep. So we're dealing with 3 significant digits across the way, so 271, right, for 3 significant digits, 271 milliliters. You might think that, oh, that's a minuscule little scenario, but it is important to convert it to some kind of standard situation so we can compare other scientific data. Do we like that number? Did we have a check on that? Okay. So there's how we can use this partial pressure. It's a tiny little step at the very beginning of the question, but then we can use it in our PV equals nRT or even our other gas law. Okay. So there are some practice problems. I'm going to give you some time to work right now on that. Whether I continue on today or not, I may do it the next day. We'll see. We'll see what the time is. I don't want to rush this next little part of the lesson as well. It's not a very big part, but I don't want to rush it either.